Class 12. The next topic is mutual induction. Now, similar to self-induction, what happens is whenever we have two coils placed side by side or very close to each other, alright, then what happens is when current is flowing through the primary coil, the first one is called the primary coil and the second is the secondary coil. So, when there is current flowing through the primary coil, there will be flux linked with each turn of the primary coil, of course. But if the secondary coil is very close to the primary coil, then due to current flowing through the primary coil, there will be flux linked with each turn of the secondary coil as well. And when there is a change in current flowing through the primary coil, then there is a change in magnetic flux linked with the primary coil. But again, there will also be a change in magnetic flux linked with each turn of the secondary coil as well. Okay, so if phi2 be the magnetic flux linked with each turn of the secondary coil at any instant, alright, and n2 be the number of turns in the secondary coil, then very similar to the self-induction phenomenon, the flux linked with the secondary coil will be directly proportional to the current flowing. More is the current flowing, more the flux linked, of course. Less the current flowing, less the flux linked. No current flowing, no flux linked. Alright, so we can write N2 phi2 is equal to capital M into I1, where capital M is a constant for a given pair of coils and capital M is called the coefficient of mutual induction, or simply mutual inductance, and thereby M is equal to N2 phi2 divided by I1. So how do we define capital M or mutual inductance from here? Mutual inductance is the flux linked with which coil? With the secondary coil, mind you, for unit current flowing through the primary coil. Okay, and again, like self-inductance, we have another definition for mutual inductance as well, which we get from here. If E be the induced EMF in the secondary coil, then E can be written as minus N2 delta phi 2 divided by delta T. Alright, so E is equal to minus delta N2 phi 2 divided by delta T. Now what is N2 phi 2? N2 phi 2 is M into I1. So therefore we get E is minus delta capital M into I1 divided by delta T. Now M being a constant for a given pair of coils, so M comes out of the delta sign. So let me do that over here. I hope you've copied these things. So therefore M can be defined to be simply E divided by, of course there's a minus sign, but the minus sign is only telling us that it has more of a physical significance, mind you. It's only telling us that the effect is such that it tries to oppose the cause. Lenz's law, mind you. So E divided by delta I1 upon delta T. So to say, we define mutual inductance to be the EMF induced in the secondary coil for unit rate of change of current flowing through the primary coil. So that is how we define mutual inductance. And as you can see, like in the case of self-inductance, the unit for mutual inductance will be Henry, because it is volt into second divided by ampere. So unit for capital M is also Henry. And by the way, I forgot to tell you, Henry is denoted by a capital H. So this is about mutual inductance or coefficient of mutual induction. Let us therefore also quickly get an expression for the mutual inductance of two long coaxial solenoids. So we have two coaxial solenoids which are wound over the same core, so to say. I have tried to denote the two solenoids by using two different colors of chalk. I hope you can make that out in the video. So I1 is the current flowing through the primary coil, N1 is the number of turns in the primary coil, and I1 is the current flowing through it. N2 is the number of turns in the secondary coil, L is the length of the primary coil. These two coils are almost of the same length. So, due to current I1 flowing through the primary coil, there will be magnetic flux at any point inside the primary coil. But since the secondary coil is also wound over the same coil, the magnetic flux or the magnetic field at any point inside the secondary coil will also be B. So therefore, B is the magnetic, it's not the magnetic flux, alright, it's the magnetic field. It's a wrong word that I've written. Okay, please do the correction like I'm doing. B is the magnetic field linked with both the primary and the secondary coil. Alright. So, can I erase this? Of course I can. Okay, I hope you all have paused the video and copied it. So therefore, magnetic flux linked with the secondary coil, linked with the secondary coil, or secondary solenoid also you can say. Let's call that phi 2. Phi 2 is the magnetic flux linked with the secondary coil, so phi 2 will be B into A, where A is the area of every turn of the loop. I think I forgot to mention this. So it is the area of each turn for both the primary and the secondary. Okay. So phi 2 is B into A, or let me erase this lower thing also. So phi 2 is, what is B now? B is mu naught N I, or rather I1 into A, simply because B is mu naught N I1. This is the magnetic field inside the primary coil 90. This is the expression for the magnetic field inside the primary coil, where N of course is the number of turns per unit length of the primary coil. So therefore, phi 2 can be written as mu naught N upon L I1 into A. So this is the magnetic flux linked with each turn of the secondary. Therefore, magnetic flux linked with each turn, okay? Each turn of the secondary coil. Therefore, N2 phi 2 is, what is this? This is the magnetic flux linked with the secondary coil. So magnetic flux linked with the secondary coil, because it has N2 number of turns, is, if we rather write, mu naught N1, this is N1 N2 divided by L I1 into A, because N, the number of turns per unit length of the primary coil, is N1 upon L, and N2 is the number of turns in the secondary. Alright, so therefore, what is mutual inductance? Mutual inductance is, according to definition, N2 phi 2 divided by the current flowing through the primary. Okay, so this comes out to be therefore mu naught N1 N2 by L into A. So this is the expression for mutual inductance for this pair of solenoids. So mutual inductance, let me rewrite it over here, is mu naught N1 N2 by L into A. So this is the expression, final expression for mutual inductance.